Welcome. Next, we're going to talk about how the singular value decomposition gives us insight into least squares problems. So our objectives are to first express the solution to the least squares problems in terms of the singular value decomposition, then look at the error in the least squares problem in terms of the singular value decomposition, and finally, we're going to use singular value decomposition to solve the problem of doing classification with orthobases. So first, let's recap the least squares problem. Recall that if we were trying to design a classifier or a model, we would set up a problem where we're trying to find W, where product of a matrix A containing data times the vector W gives us the vector D. So D is an n by 1 vector, A is an n by p matrix, and we've assumed that the rank of the matrix A is equal to p. Well, we've seen before that the solution in this case is to set W equal to the quantity A transpose A inverse A transpose D. And that results in a D hat, which lies in the plane defined by the span of the matrix A, given by A times W, or equivalently A times the quantity A transpose A inverse A transpose D, which is just the projection of D onto the space spanned by A. So we take some vector D, shown in orange here, we drop a perpendicular line to the plane, and that gives us the approximation D hat that results when we solve this least squares problem. The error is just the difference between D and D hat, and the error is exactly what we're trying to minimize the 2 norm of in this least squares problem. And this error thus can be written as D minus PA times D, or a matrix we've called PA perp times D. So PA perp is the projection of D onto the space orthogonal to the matrix A. So that's the projection in the normal of the plane here, which is where E lies. So what we're going to do now is use the singular value decomposition for A. And I want to explicitly write this singular value decomposition in the full SVD. So A is taller than it is wide, which means U is an n by n matrix, and we can divide that into the first set of columns associated with non-zero singular values that span the space associated with the columns of A. We'll call those U tilde, and then we'll have the remaining n minus p columns, and we'll put those into a matrix called U perp. So this first part on the left here, U tilde, is n by p, and U perp is n by n minus p. And U perp, of course, when I multiply into these block of zeros here below the diagonal matrix of singular values, this U perp goes away. So we can also express A in terms of the economy singular value decomposition, U tilde sigma V transpose. Remember, sigma is a diagonal matrix with singular values along the diagonal, ordered from largest in the upper left to smallest in the lower right. So first we're going to substitute for A with the singular value decomposition in the expression for the least squares weights. And so that's going to give me V sigma transpose U tilde transpose, U tilde sigma V transpose, whole thing inverse times V sigma transpose U tilde transpose. So clearly here, V sigma transpose U tilde transpose is what's representing A transpose. Well, we can recognize that since the columns of U tilde are orthonormal, U tilde transpose U tilde is the identity, and since sigma is a diagonal square matrix, sigma transpose is equal to sigma, so we can reformulate this expression for the weights as V sigma squared, so that's sigma times V transpose, quantity inverse, V sigma U tilde transpose D. Now for our next step, we're going to simplify the inverse of this product of 3 matrices here. Recall that if I have a product of 3 matrices where each matrix is invertible, then the inverse of the product is the product of the inverses, just in the reverse order. So here, these 3 matrices are invertible since V inverse is equal to V transpose because the columns of V are orthonormal. And sigma is a diagonal matrix with the singular values, which are all greater than 0 on the diagonal. So when I apply this formula for the inverse of this product, I end up with V, so that's the inverse of V transpose, sigma inverse squared, V transpose, which is the inverse of V, times V, sigma U tilde transpose times D. And again, we can simplify V transpose V because that's the identity, and we can multiply sigma minus 2 times sigma, which I've done over here on the right, sigma minus 2 being 1 over sigma 1 squared, 1 over sigma 2 squared, and so on, with sigma being sigma 1, sigma 2, sigma p. These are both diagonal matrices. When I multiply these, I just end up with 1 over sigma I on the diagonal, so this is sigma inverse. So we end up with W being equal to V sigma inverse U tilde transpose times D. Now I can expand this out in terms of the individual components, since sigma inverse is a diagonal matrix, and this becomes the sum I equals 1 to P, 1 over sigma I, V sub I, times the quantity U tilde I transpose D. So this is the inner product of the ith left singular vector with D, and V sub I is the ith right singular vector, and these components are weighted by the inverse of sigma sub I. Now this expression for A transpose A inverse A transpose that we've arrived at, writing it as V sigma inverse U tilde transpose, this we can also call the pseudo-inverse of A. And you can verify, of course, that if I multiply this pseudo-inverse by A on the right, that I get the identity. We have that, of course, in the original form with A, and similarly, when we do the singular value decomposition for A, we obtain the exact same result after using the properties of the singular vector matrices and the singular values. So now we've solved for the least squares weights. Let's look at the least squares error and see how this relates to projection matrices. Recall that we're trying to approximate a vector D, and our approximation has to lie in the span of the columns of A. So that gives us a vector D hat, which lies in this plane that we've illustrated. And then E is the vector normal to the plane that terminates at D. So we can write D hat as A times W, which I've expanded out here in the form that we had previously. This is just the projection of D onto the space spanned by the columns of A. Now if we substitute the singular value decomposition for A on the left and this pseudo-inverse, which is in the square brackets down here, we have that D hat is U tilde sigma V transpose times V sigma inverse U tilde transpose times D. Again, taking care of the algebra, we recall that V transpose V is the identity, and then we have sigma times sigma inverse in the middle. That just gives us the identity. And so this all simplifies to U tilde times U tilde transpose times D. And this implies that the projection matrix onto the space spanned by the columns of A is also expressed as U tilde times U tilde transpose. So the span of the columns of A is equivalent to the span of the orthonormal basis for the columns of A, which is exactly what the left singular vectors in U tilde represent. So we can project onto A, or we can project onto the space spanned by U tilde, and it's equivalent because those are the same spaces. The expressions differ slightly because U tilde has orthonormal columns, whereas A does not necessarily have orthonormal columns. So if you look at the error is going to be the difference between D and D hat, which we could write now using this new expression for the projection onto the space spanned by A as I minus U tilde transpose times D, and this is just this projection onto the space orthogonal to A. So we have the plane representing the space spanned by A, and then we have E lying in the space orthogonal to that plane, which we can represent as a projection onto A perp times D. Now, this projection then can be expressed in terms of the left singular vectors as I minus U tilde transpose. Well, recall that we started by defining the full singular value decomposition and also had the economy singular value decomposition represented by the left singular vectors u tilde. U, being the full set of singular vectors, is an n by n matrix, and we know that since these are all orthonormal and there are n of them, that U transpose U is equal to U transpose, which is the identity, and we'll write out U transpose in terms of this partitioned matrix representing the left singular vectors associated with non-zero singular values, and then these terms which are associated with the block of zeros in the sigma full matrix. So this is U tilde, U perp, U tilde transpose, U perp transpose, and multiplying these block matrices gives U tilde transpose, which is written down here, plus U perp transpose. So if I subtract U tilde transpose from the identity on the left, then I'm left with U perp transpose, and that's exactly has to be equal to the projection onto the space PA perp. So this projection is equivalent to using the left singular vectors that are orthogonal to the space spanned by columns of A. Lastly, look at how singular value decomposition helps us doing classification in terms of orthonormal bases or orthobases, as we referred to in the previous unit. So recall, in a classification problem, we have a training step where we take these features that we have associated with known labels, and we set up this least squares problem, AW equals D again, and then when I observe some new feature, x tilde, I take the inner product of x tilde with W and then take the sign of that, and that gives me my prediction for my binary classifier. Now the singular value decomposition of A gives us a natural set of orthobases, and those are represented by U tilde. So if we solve the classification problem in terms of these orthobases U tilde, it becomes U tilde W prime equals D. And since U tilde has orthonormal columns, we obtain W prime is simply U tilde transpose times D. Now recall, one of the reasons for using this orthobasis classifier is that all of the columns of U tilde have the same norm. The ith column of U tilde multiplies into the ith weight W prime, and therefore, since these columns all have the same norm, we can look at the magnitude of the weights, Wi prime, and that will indicate the importance of the ith ortho feature. It's harder to do that with the columns of A because the columns of A in general are going to have different norms, and just looking at the relative size of the elements of W doesn't really tell us which of these features might be super important and which might be relatively unimportant. But in this case, because all the columns of U tilde have the same norm, I can look at the relative size of the W primes, and that tells us the importance of the feature. So that's a big rationale for using orthobases, is it's very easy to determine which features make the biggest difference in terms of the predicted label. Now there's a relationship here between W and W prime, and this is obtained simply by looking at the singular value decomposition of A. Clearly W has to be equal to V sigma inverse U tilde times D, or V sigma inverse W prime. And this relationship allows us to do orthobases classification using a new feature, so predicting the label associated with a new measured feature that wasn't used for training. So originally we were going to do the prediction problem, Y tilde. The predicted label is the sign of this new feature, X tilde transpose, inner product with the weights W. Substituting for W in terms of W prime, I can write this as the sign of X tilde transpose times V sigma inverse W prime, using the expression we had in the upper right. So what we're going to define is a transformed feature, X tilde prime transpose, being equal to X tilde transpose times V times sigma inverse. And then our orthobasis classifier is simply the sign of x tilde prime transpose times w prime. Implement this classifier in either the orthobasis space spanned by u tilde or the original space spanned by a, and it simply amounts to using a different set of weights, w prime versus w, and transforming the measured features from x tilde to x tilde prime. So if we want to prune features by removing elements of w prime that are very small, it's very easy to do that here, and clearly it's going to eliminate the features in x tilde prime corresponding to values of w prime that are very small.